One force that every single type of molecule has, though, is the dispersion force or London forces. This applies even for non-polar molecules. Here we see a helium atom. A helium atom has 2 electrons. Now, generally speaking, on average, we expect these electrons to be basically evenly distributed. It is non-polar. However, who is to say that in a particular instant you can't see both electrons on the same side of the helium atom? Then we have created an instantaneous dipole. At that instant, this end of the helium atom is partially negatively charged, while this end is partially positively charged. What happens when that happens? Well, what happens is that the electrons in the next neighboring atom get attracted towards the partially positively charged end of this particular atom, and so these atoms attract one another. So what determines the strength of these forces, which are relatively weak but important because they're everywhere? It turns out it depends on the polarizability of the molecule, which basically means how easy it is to generate a dipole in this molecule. Generally speaking, as a first rule of thumb, we can consider the molecular weight. As the molecular weight increases, typically there's more electrons that can delocalize, and therefore it's easier to have a temporary dipole. One common mistake, however, for beginners is to assume that molecular weights determine the strength of intermolecular forces entirely. In fact, they do not even determine entirely the strength of London forces. We can consider 2 isomers of pentane. In other words, they have the same formula and therefore they have the same molar mass. However, N-pentane here has a significantly higher boiling point than neopentane. Why is that? It turns out that this is a longer molecule, and as it is a longer molecule, basically there is a better chance for the electrons in it to separate in a way that creates an instantaneous dipole across the length, so that's a stronger dipole. And then if you have neopentane here, where it's kind of more Bohr-like, and so the London forces are stronger in N-pentane than in neopentane.